Today we are going to prove an important theorem, that is outer measure of an interval is equal to the length of the interval. So that is the second theorem of measure theory. So that is one of the fundamental theorem. So let us see. The outer measure of an interval equals its length. So let us prove it. We are going to break up the proof into cases. Case number 1, we are going to take the interval to be a closed interval, closed and a finite interval AB. So if we take an arbitrary small number epsilon, then the interval closed on the left and the open on the right, that is A, B plus epsilon contains I. That is quite obvious. That is, closed interval AB is a subset of the interval A, B plus epsilon. So since this one is a subset of this one, outer measure of this one will be less than or equal to outer measure of this one. So that is quite clear. Outer measure of this one is less than outer measure of this one. And then so A is a subset of B. That theorem implies outer measure of A is less than outer measure of B. We are applying that theorem. Okay, so here let us see. So this A, B plus epsilon is in the collection of all covers of A, B plus epsilon. So when you talk about a collection of cover of A, B plus epsilon, A, B plus epsilon itself is a member in the cover. Okay, then you are taking the infimum. Therefore outer measure, that is the infimum, will be less than or equal to length of the interval B minus A plus epsilon. Alright, so then what do we have? We have this inequality. Outer measure of the closed interval FB is less than or equal to B minus A plus epsilon for every positive number epsilon. Then we want to establish the relationship between M star AB and B minus A. So there are three possibilities. M star AB is exactly equal to B minus A, or M star AB is less than or equal to B minus A, or M star AB is greater than B minus A. That means if these three possibility, if we assume that three possibility, does this inequality hold for every epsilon? That is the thing we are going to find out here. So let us see. This is M star AB, this small rectangle, it is M star AB, and then this is B minus A. So this is the case when B minus A, that is length of the interval, is exactly equal to M star AB, that is outer measure of AB. Alright, so in this situation, if you put here something additional epsilon, okay, so obviously the total length is greater than this one. That means this one is greater than this one. So this inequality holds when M star AB is exactly equal to B minus A. Alright, next, suppose length B minus A is greater than M star AB. In that situation, if we put some additional epsilon here, so it is also obvious that this total length is greater than this one. That is, this inequality is true. B minus A plus epsilon will be greater than or equal to this one. This inequality is true when we assume that B minus A is greater than M star AB. Alright, but in the last case, suppose M star AB is greater than B minus A. That means this is greater than this one. But if you put here something additional here, this much epsilon, then obviously this length is less than this one. That means this inequality fails to satisfy when M star AB is greater than B minus A. So therefore what we conclude is that if these inequalities hold true for every arbitrary epsilon, what is the conclusion we can draw? We can draw that M star AB is less than or equal to B minus A, but B minus A is the length of the interval, closed interval AB. Let it be inequality number 1. So next we obtain the reverse inequality or opposite inequality. That is, M star AB is greater than or equal to B minus A, and that is length of the interval AB. Okay, so from the definition of outer measure, for every such positive epsilon there exists cover in of I by intervals such that m star AB will be greater than or equal to summation n going from 1 to infinity length of the intervals in the cover minus epsilon. So where in is equal to b minus an, close on the left and open on the right. Okay, so from each n then we form this type of open interval an minus bn epsilon minus epsilon divided by 2 to the power n comma bn. So then you get this one. So let us see this formation. We are going to calculate this formation. So for that let us use this one. We have this interval, we have this interval. All right, so here an is here bn is here. So this is closed here and then it is open here. So from an we are going to subtract a small positive number to the power n, epsilon by 2 to the power n, and then it will be somewhere here. Okay, this is what? This is an minus epsilon by 2 to the power n. Then you have this open interval here. Okay, so this open interval we call it in prime. This is in prime is equal to bn. So the earlier original interval is in, this is equal to an, this one bn. All right, so from the figure also it is obvious that in, it is a subset of in prime. Okay, so what is the length of the original interval? Length of the interval lin is equal to this is equal to bn minus an. And what about the length of the interval, new interval, open interval, and prime? This is equal to so bn minus an plus epsilon by 2 to the power n, but this quantity is equal to this quantity, so you can put this is lin plus epsilon by 2 to the power n. So suppose if you put summation both sides, summation n going from 1 to infinity here, then you will put summation here also, summation n going from 1 to infinity for both this term. So this is equal to, this one is summation l going from 1 to infinity lin here, and this one is, this is a geometric series, summation epsilon by 2 to the power n is going from 1 to infinity. This is a geometric series, and this is equal to epsilon, summation n going from 1 to infinity lin. So this is equal to epsilon. So these facts are there for the interval in and in prime. Okay, so then having that fact in the background, we'll have this one. So in primes are bigger than in, so union in is a superset of I, therefore union in prime will be also superset of I. So but in primes is an open cover. Okay, it is open interval, so collection of in prime is an open cover for the closed and bounded set I, that is a comma b. So we know that this set is compact, so by compactness there is a finite subcollection. For this, from this collection we will be able to find in the finite subcollection. Let the finite subcollection be called as j1, j2, j3 up to jn, which covers I. So then we can put jk is equal to ck dk. Alright, so and then I is a subset of the union k running from 1 to n. So what we have, let us again see this one. So this is your closed interval AB, this is the closed interval AB. Since this is compact subset of R, every open cover of it will have a finite subcover. So finite subcover are J1, J2 and Jn, something like that. So finite subcover will maybe like this one. Suppose this is J1, and then suppose this one will be J2, right? And then this one will be J3, like that, okay, and keep on going on like this. So then this one will be suppose here, and then suppose this will be so many things. Some may be here redundant, that means that is even if you remove that one, the remaining will still cover the this one. So AB is a subset of the cover of this one. So suppose this is C1, then the leftmost point will be C1 here, and suppose this is the interval, last interval is C and D, and then this point will be the N, like this one, okay. So the union J1, J2 up to Jn, their union will be this set, okay, this set, their union will be this set, and length of the union will be, what is the length of the union? So Dn minus C1 will be the length of the union here. But if you take the individual interval and find the length and the sum of, so C1 will be here, and then C2 will be here, okay, and then C3 will be here. You are going to sum up the length of the interval, so it will be like this one, and then C3 will be, C4 will be there, and then lastly suppose Cn and Dn will be here, okay. So what is the thing we can understand from here is that if you take the individual interval length and the sum of that will be bigger than the union's length. The union's length will be less than the, if you take the sum of the individual interval, that will be greater than the length of the union, okay. So that is quite obvious, okay. So let us see then, this one, you have this collection, okay. They are named as JK, CK, DK, and their union will be superset of I, okay. So yeah, this is the collection. From this one, some other redundant member are there. Even if you remove them, the remaining will be still a cover of the closed interval I. So we can remove the redundant one, okay. So this is the closed interval. Let us see again. This is the closed interval, all right. So these collections, they are finite subcollection. Their union will be superset of the closed interval AB, all right. So if you take the length of the individual interval, you have this much length from here to here. So from here, the redundant one, this one, even if you remove this one, the remaining will still cover, okay. So we can remove that one, and then suppose you take union, right, you take the union of this interval, that length of the interval is from C1 to the N, that is Dn minus C1, okay. So from the picture it is very obvious that this one, that is sum of the length of the interval will be greater than length of the union of the interval, okay. And the redundant one from here also you can remove, because if you even remove that one, the remaining will be still a cover of the closed interval AB, okay. So this is the sum of the length of the interval, all right. This is the length of the union of the interval, that is Dn minus C1, okay. So we may suppose that JK is contained, no JK is contained in any other, that means we have removed the redundant one. Then supposing that C1 is less than C2 and so on, Cn, so what do we get? That is the length of the union, that is exactly equal to this one, that calculation you can make it easily. So length of this union is exactly equal to this one, and this one will be less than the length of the sum of the sum of the length of the intervals, individual intervals. So we have, what do we have? That the outer measure, that is greater than or equal to summation n going from 1 to infinity Lin minus epsilon, okay. So that is coming from the inequality number 1. So that will be greater than or equal to summation n going from 1 to infinity minus twice epsilon. So equality is there, that is you can write like this. So suppose when you convert length of the interval In into length of the interval In prime, minus epsilon will be there. I have already explained that one. So here is minus epsilon, here minus twice epsilon, but this one, summation is going from 1 to infinity, and this one is summation is going from 1 to capital N. Therefore obviously this term will be greater than this one. Okay, so that means from here again, from here, what is this? This will be, I have already shown that greater than the length of the union. Okay, the n minus c1, and minus twice epsilon is also here also. So but this one will be still greater than length of the interval. That also I have shown it, b minus a minus twice epsilon, but this is length of the interval, this one. So ultimately what you get? Outer measure of the I is still greater than length of the interval minus twice epsilon. Here again minus twice epsilon. Epsilon is any arbitrary small number, so you can remove this one. So what is the conclusion? Therefore m star I is greater than or equal to length of I. Let it be inequality number 1. Combining inequality 1 and 2, what is the conclusion? Outer measure of the closed interval, closed and a finite interval, is equal to length of the interval. So it completes the first case. So next, case number 2. For the case number 2, suppose we are going to take the interval in this form, open on the left side and close on the right side, and suppose a is never minus infinity. Okay, a is not minus infinity. So in case a is equal to b, then this interval is going to be an empty interval. We know that empty interval has length 0, and so empty set also measure 0. Therefore, so in this sub case the result is okay. Therefore we are going to consider the sub case where a is not equal to b. Alright, so that is a is strictly less than b. Then you take an arbitrary epsilon such that epsilon is less than b minus a, that is the length of the interval. Then you put here I prime is exactly equal to, you put I prime equal to closed interval a plus epsilon b. So this is closed interval. For closed interval we have already proved the theorem, and obviously it is seen that I prime will be a subset of I. Alright, so then outer measure of this one will be less than or equal to outer measure of this one. That is what we are writing here. So but the I prime is closed interval. For closed interval we have just now proved that outer interval is the length of the interval. What is the length of the interval? B minus a minus epsilon is the length of the interval. That will be less than this one, and this inequality is true for every arbitrary epsilon. So therefore what we can conclude is that length of the interval, that is b minus a is the length of the interval, is less than or equal to outer measure I. Let it be inequality number 3. So then you put I double prime is equal to a b plus epsilon. This is the interval. So then in this case also I is a subset of I double prime. Then outer measure of I will be less than or equal to outer measure of I double prime. That is what we are writing here. But outer measure of I double prime will be less than or equal to b minus a plus epsilon for any arbitrary epsilon. Okay, this one also we have explained earlier. So it follows that for every arbitrary epsilon it is true. Therefore it follows that outer measure of I is less than or equal to b minus a, that is length of the interval. Let it be inequality number 4. So from 3 and 4 we get outer measure of I is exactly equal to length of the interval. So that is what we wanted to prove. We have done case number 2. So case number 3, in this case we are going to take the interval is an open interval AV. So AV are finite, so if you put back b here, then this will be a superset of I. That is obvious, I is a subset of this one. Therefore outer measure of this one will be less than or equal to outer measure of this one. So that is what we are writing here. But for this one we have just shown that outer measure is equal to b minus a, that is length of the interval I. Okay, let it be inequality number 5. Alright, so for arbitrary epsilon that is less than b minus a, we have this set will be a subset of this one. Okay, so if you subtract something from b and that subtraction is less than b minus a, that is length of the interval, that this set is going to be a subset of this one. Therefore outer measure of this one will be greater than outer measure of this one. that is m star I will be greater than or equal to m star a b minus a. But for this one we have shown is equal to length of the interval epsilon, that is m star I is greater than or equal to b minus a, that is length of the interval. Let it be inequality number 6. From 5 and 6 we have the inequality. M star I is exactly equal to b minus a, that is length of the interval. Alright, so case number 4, lastly we are going to prove for infinite interval. So interval of this form, I is equal to close on the left and open on the right, where a, b are finite. Then from the definition it is very clear that m star I is a subset of it is less than or equal to b minus a, that is length of the interval. Okay, this one also I have already explained that one. For the reverse inequality, you take an arbitrary epsilon that is less than the length of the interval b minus a. Then as I have explained earlier, this set is going to be subset of this one. Therefore outer measure of this one will be greater than or equal to outer measure of this one. So outer measure of this one is greater than this one. But for this we have already shown outer measure of this one is equal to length of the interval, that is b minus a minus epsilon. This is true for every arbitrary epsilon. Therefore m star I will be greater than or equal to b minus a, that is length of the interval. Thus we have this inequality, okay, the equality that we have just now proved. So the last case, in the last case we are going to take that I is an infinite interval. So infinite interval can be of the following possibilities. Number 1 is minus infinity a, that is open infinite interval. Number 1 is minus infinity a, that is closed infinite interval. This is infinite interval on both sides, and this is closed interval. Okay, and this is just open interval of this form. So we take one of the case and the other case follow similarly. So let us take this one, I is equal to minus infinity a. Let us take it. Then for any positive number, you can take 1 billion or 2 million or like that, any big positive number that is greater than a. You take any positive number that is greater than a, we have what we have. So minus infinity minus m a, this is open interval, is a subset of I. This one is a superset of this one for any m minus m, that is true. So therefore outer measure of this one will be less than outer measure of this one. So we want to find out the outer measure of this one, and we want to show that outer measure of this one is equal to infinity. So outer measure of minus m a, this is going to be a finite interval. It is less than, for finite open interval we have proof what is the outer measure of this one, that is the length of the interval, that is a plus m. So a may be any negative number or positive number, but here you are adding any big positive number. So this can be regarded a very big positive number. So this is going to be greater than any big positive number. This is going to be greater than any big positive number. So in real number, a number which is greater than any big number, that is going to be the infinity only. So therefore m star I is equal to infinity. Okay, so like that we have just proved